Here today is Leonardo Cruz from IPhT Saclay. Tell us about the classical offshell currents.
Thanks. So first, just let me thank the organizers for the invitation to speak here. So it's a pleasure to be here in Sao Paulo and also at this nice institute. So, today I'm going to talk about the work that I did in collaboration with the PhD student in Bologna, Francesco Converiati, and which we presented last December. So the talk is going to be organized as follows. So in the first part, I'm going to give a motivation of why I think it's important or interesting to study offshore currents, and in particular the classical limits, and also introduce the currents, so the objects that we are going to study. In the second part, I'm going to give a review of world IPFT, because one of the main goals of this talk is to show that there is a relation between offshore currents in the classical limit and the partition function of world IPFT. So, as far as I know, the topic of world IPFT has not appeared in this workshop. So, I'm just going to give a review and show the main points of the formalism. So after doing that, then I'm just going to show this relation. I said world IPFT and these offshore currents, and then I'm just going to show how to compute them. So changing gears a bit, I'm going to show another application of these currents in the area of high temperature QCD, right? So in the limit in which the classical limit is relevant. So that's going to be the fourth part, and finally I'm just going to conclude. So very good. So first, the motivation. So of course, the reason why we're here is because there is a communication between Amplitudes communities and gravitational waves communities. So the overall motivation has been given in many talks, so I'm just not going to repeat that. So that's the advantage of being in the third week. So you can just check talks by Ricardo, Mao, both Ricardos, Mao, Justin, and so on. So instead, let's give a motivation from the point of view of amplitudes of why in general offshore currents appear. So, so we know that the goal in life of scattering amplitudes is to be part, an important ingredient of the calculation of observables in colliders. So here, this part is what they appear. So, so there are many methods that have been developed over the years. Spin-helicity, these are just keywords that have also appeared in some talks. What these methods are and how they have been developed to be used in this calculation of observables. So, so this is of course an oversimplified story, but eventually the knowledge of amplitudes ends up being coded in event generators. And in these event generators, usually in some of them, what is employed are parent-linear recursions, offshell currents, which eventually can be used to recover full amplitudes. So this is the use of offshell currents in the story of collider physics. So we have seen also in Fernando's talk that offshell currents, as the number of particles increase, tend to be more efficient than the onshell approach. Okay, good. But so yeah, you may ask, for gravitational waves, we only need up to n+5. So why are you even bothering of computing more than n=5? Sure, that I would say that is a valid complaint. So yeah, perhaps not for gravitational waves, but what about finite T? And this is the second application that I'm going to show, in which I'm going to argue that in these applications, the classical limit of offshell currents for higher number of particles is relevant. Very good. So what are offshell currents? So, so the definition that I'm just going to give is think about all the diagrams, Feynman diagrams that contribute to an amplitude in which you have n plus 2 particles, where 2 of the particles are massive and they're on shell, whereas the n particles that are gluons or any gauge bosons, for example, are massless and they're off shell. So this is the definition of an off shell current. So this is a slight generalization of a Ferenczi current in which only one of the particles is off shell. So as usual, the amplitude can be recovered by dotting with the external wave functions of your amplitudes. This might be polarization vectors, or also you can allow, of course, because we are also thinking about Young wheels. So the indices here represent color indices that might appear in the current. So, so to visualize these currents, you can also see some of the diagrams that appear in the currents at an exhibition at the Museum of Art in Sao Paulo. So there are some diagrams by this artist that I'm not going to even try to pronounce this name, but you can see some of the diagrams that contribute this current for higher points. So apparently this artist just was inspired on drawings that people carry on the bodies. So if you're interested, just please go and check the story.
It's inspired by one.
No, you might think that it's inspired by that, but no. Very good. So after this brief deviation, so let's start with so what's Worldline IPFT? So the word Worldline appears in many contexts. So I think it's also worth stopping a bit and notice what's this word Worldline that I'm using. So we heard about the Worldline IPFT that was discussed in Ricardo's Sturani talk. So, which is the use of this method, the effective field theory to the study of scattering or bounded systems. So there's another Worldline, which I'm going to call Worldline IPFT1, which essentially goes back to Feynman and Schwinger and the developing of propagators as a path, a Worldline path integral. So there's a review by Schubert that you can check if you are interested from 20 years ago, what Worldline. And the Worldline that we are interested in discussing for a bit is Worldline IPFT2, which is based on the first one. Okay. So the story starts like this. So first, so what I'm interested in describing is a particle, scalar particle, which is moving in a background, in a gravitational field. So then the field theory action has two parts. So one part, which is the Einstein field reduction, and the other part, which is the action that describes matter coupled to gravity. And in addition, there is a term that is also included here, which is a non-minimal coupling between the curvature and the scalar particle, which is there for consistency on the Worldline. So very good. So then from the matter action, I can use integration by parts and write down a Hamiltonian operator, from which using Schwinger trick, I can express as an integral over this t, which is sometimes known as the Schwinger proper time. So the next step is to interpret this Hamiltonian as a particle Hamiltonian, which I do by setting the derivative as just the momentum. So I recover the Worldline action in phase space with an addition of a Lagrange multiplier, which is usually known as the Einbein. So from there, I can construct the action in position space, which is configuration space, which is just the second action shown here. So very good. So once I've constructed my action and using the trick of Schwinger, I can express my my propagator, the propagator that I'm interested in, as a Borland path integral. Yes.
Could you go back to the previous slide, please?
Yeah.
So the Hamiltonian, it seems with the expression that you give in the second to be a invariant quantity. I mean, shouldn't be like the energy?
Yeah, it's energy. Yeah.
But I cannot understand that you have in fact that instance meaning. I mean, it's the zero components. You have component energy momentum. So it's the zero component. It shouldn't be something.
This is the Hamiltonian operator. I'm just going to interpret after as the energy. This is the part that I'm doing here. See that you are following.
That's it.
Yeah.
It's not the energy. It's not the right units, but it's a function that generates the dynamics. It's not the energy.
Okay, good.
It's separate.
Okay, very good. So then, then using the expression that Schwinger gave to us, I can then re-express the propagator as a Borland path integral. So because we are doing GR and I'm using the image of having a point-like particle, so I need to include I have to make the mesh translationally invariant, which means that I have to include the what is called as Lagrange costs, which is something that is highlighted in red. And in addition, there are going to be UV divergences in the definition of the Borland, exactly because I'm having a point-like particle, which are not related with the UV divergence of GR. So for that, I also need terms that are regulators. Very good. So, and with this expression at hand, I can do perturbation theory. So, and the perturbation theory I'm thinking is the perturbation of the whorl line along the straight line, and where I'm perturbed with respect to this variable q. So the integration of the path integral then is just going to be with respect to q, which I can think as a fluctuation with respect to this to the straight line. And once I use perturbation theory, then I can think of this dress propagator as a resolution of all diagrams that contribute to a certain amplitude. So if I have two external gravitons, then I can think of the dress propagator as the sum of all the possible Feynman diagrams. Of course, here I'm doing tree level. The form diagrams that contribute to this current with two gravitons. But of course, this object is still off shell. So and I'm interested in the case when the massive particles are on shell. So what I have to do is just to amputate the just propagator, which means just perform the usual LSZ procedure to do. So this is shown in the bottom line. So I can do this, and I use my perturbation theory and so on. So this is fine. This is something that you can, for example, if you're interested in checking Christian Schubert's review. But okay, but there is a shortcut to do that. This is a prescription that goes back to Fradkin, 60s. And that was also used by Fabricesi, Petrino, Veneziano, and Bukovitsky in 1993. And the prescription tells you that to recover the amputated propagator, what you have to do is to replace the limits of integration of your action that here go from 0 to t in the action that's in the bottom line. So the limits of the integration go from -infinity to +infinity, okay, and essentially drop the integral of the Schwinger product type. So this is something that can be checked order by order in perturbation theory, and this is the one of the main points of the work by Gustav Noel, Jan Lefka, and Jan Stein, which from now on we're just going to refer it as the Berlin collaboration, because Gustav and Jan are at Humboldt University of Berlin, and Jan Steinhoff, I think, is at Potsdam. So this is what they show, and they also told us that the equivalence between these two procedures is encoded in this very important relation, in which on the right-hand side I have the connected trace propagator with the external massive lights on shell addressed with these factors. Okay? And on the left-hand side, what we have is precisely what I just told you. So it's just essentially the action in configuration space with now the limits of integration, time integration go from -infinity to +infinity. So here I'm writing down with the slightly more general version, because this is essentially a relation that you can check for any theory in which you can construct a trace propagator. So the background can be a background of gluons, a background of gravitons, and so on. So for this example, of course, the background is just the background of gravitons. And here I'm also showing an additional integration with respect to auxiliary variables, which might appear in your Worldline action. So these auxiliary variables can help you to work with the degrees of freedom, which are the spin, which will be related with spin, but can also be auxiliary variables that you introduce into your action to deal with color degrees of freedom. Okay? So the general form of the partition function that I'm going to be interested in has this form. So as I said, this relation exists for essentially any WQFT construction that you know. So for models in which you have n equals 1 or 2 super symmetries on the Worldline, okay, so, which can be used to model spin, classical spin. Okay. We've also done the case in which you have a photon in the background of gravitons. You can also construct this partition function, and also with color theories. Okay. Very good. So when you have done construct your partition function, then the rest is just developing final rules for you to compute the path integral. So meaning that now we are doing a path integral with respect to the background and the Worldline variable, which means that I'm going to have a propagator for the Worldline and a propagator for the gravitons. And in addition, I'm going to have some vertices that tell me how the gravitons and the Worldlines interact. And the perturbation theory in this case is controlled by the number of the powers of Q, of the fluctuation variable. Of course, as I said, there's also graviton vertices. And then just turn on your machine and do calculations if you are feeling like doing. So very good. So now how this is related to amplitudes. So the relation was outlined a long time ago in this paper. So and the idea is, I mean, think about the correlators. Think about a correlator. So in this case, now I'm thinking about two particles. So I'm just thinking about a correlator for fields, for scalar fields, again in the background of gravitons, and then I have the two particles, two fields which carry different masses. So for this example, so I write down the path integral, the field theory path integral of this correlator, which is just from standard field theory. It's the expression on the top. So, and the approximation, which is the usual classical limit that people used to think always, which is just considering the tree approximation, it's essentially equivalent to using the path integral of the scalar fields to write down the 2-point function as precisely the dress propagator. So that's the key relation. This implies that I'm just considering diagrams in which there are no loops, there are no internal loops, there are only trees, which can be also disconnected. So from this expression, then I can simply pass to Fourier space and compute my amplitude in the classical approximation. Okay, so then the next step is relatively straightforward. Then I move to impact parameter space by doing another transformation, and I recover the icon of phase. The explanation of the icon of phase is precisely the partition function. So that's what that's how this approach is related with amplitudes. And it's shown in the figure, but you can also consider external parameters. So just by adding your correlator, so gravities as well, and you can do that for arbitrary number of gravities. So good. So once we know about this, some key aspects of Polar QFT, let us move to the case at hand, which is the optical currents. So, okay, and I'm interested in the classical limit of this object that I defined at the beginning. So I'm interested in having a notion of the particle which is on shell moving in a trajectory in which there is definite position and momentum. So how do I do that? So there's some notion of classicality that has to be imposed in my current. So this notion, well, it's not very surprising, but what I have to do is to think about coherent states. Particle that I'm working with having a wave function that is coherent in some sense. So this sense that I'm thinking about the particle as being in a coherent state is a sense that was developed a long time ago by Perel'emov that told us how to construct coherent states for a particle that carry mass for an arbitrary Lie group, actually, not only for the groups that we are interested in physics. So for any Lie group, you can construct a coherent state, essentially. So for the case at hand, I have a massive particle. So what I'm interested in is to construct a coherent state of the restricted Poincare group, which has this form in general, the form that is shown here. Okay. So what is important is that there is a complex parameter here, which is Z here, which if you are used to think about coherent states in the usual representation in terms of creation and annihilation operators, you know that there is also a complex parameter that pops out there. Actually, by definition, you have it there. So this is the same complex parameter that you have in your coherent state. So with this, in fact, you can also check that the wave functions that appear in formalism by KMOC correspond to the special case in which you have the complex parameter has this form. Very good, but of course, what the formalism by KMOC is a formalism of observables, but shell currents are not observables. So what do we do? Yeah, so with this, I have thinking that there are not observables, but nevertheless, I'm just going to define this object, which is the off-shell current that I defined before, but dressed with coherent states functions. So this is what I have here. So now what I can do is now remembering that my off-shell current has a part on the direct delta that encodes the momentum conservation. So I can solve for this integral. And I use the integral to obtain the current, the current that is here in blue. And after that, well, I restore powers of h bar on my variables which carry which are massless. Just as I did, just as I would do in the case of the KMOC, and then think about an expansion of powers of h bar. So the second integral looks a bit involved, but the real form is the one that is shown here, which can be solved. And after solving this integral, you you find that the expression, this object formal object that I defined, just given by these expressions. So what you notice is that the overall effect of weighting these coherent wave functions is to obtain this factor that looks a bit strange. Not too strange to you because you saw it before in the introduction of the IPhT. So at this point, I'm focusing on tree level. So this is a tree level object. Okay. So and once I've defined this current and found what this expression is, so I can find this the relation between IPhT and off-shell currents that you can anticipate by the form of the current. So very good, very good. So for concreteness, I'm just going to take QED. So and I'm going to think about the QFT path integral that defines the off-shell current. So again, I'm thinking about the correlator to scalars, so scalar QED. So I have also scalars, my theory. So scalar QED, I have massive particles and I have massless particles. Okay? But I'm keeping the massive particles option. So this is something I can do. So what you do in QFT, you usually use the LSF reduction and just strip out the external particles. So I'm going to do the same, but now I'm going to keep the external particles of shell, which is what I'm doing in the line in blue. And I'm already taking the classical limit. So this means that I'm already associated the field theory path integral of the two scalar particles with the dress propagator. So this expression is just the classical limit of this current, of the current without the direct delta. So I can use this path integral into my definition of the current, okay, and construct the object below. So and the terms highlighted in red, are just exactly what I found in my general relation between the connected on-shell dress propagator and the propagator written in terms of the action with the limit integration from -infinity to +infinity. So this means that the path integral representation of the current is just simply being that it's here it's part of what is highlighted in red here. So it's this expression. So which means that the off-shell currents is nothing else but the expectation value of an arbitrary number of photons in this case with respect to the partition function of world IPhT, which I'm writing here. So there is a similar story that you can develop for full KMOC and world line formulas. This is something that appeared a few weeks ago, I think, this paper by Damgar, Hansen, Lampe, and Van Hoff. can also find this relation between full KMOC for observables and path integrals, in particular the word-line formalism. So, but the take-home message of the story that I'm telling you is that for the specific case of off-shell currents, addressing the off-shell current that you have, that you know from IPFT, it's enough to construct the Euler representation of the current from Euler IPFT. So that's the relation. It's a key relation. And of course, you can now do calculations in any theory that you like. So, for example, we have done some calculations with QED. So notice that that because I integrated over one of the delta function, the current now depends on only a single momentum, which is just called P here. And this is again an off-shell current in this guise. And notice that also the amplitude that I need at the end of the day to do calculations is the term in parentheses. So you can do play the same game, just calculate, just put it in the computer and do 7.3D current if you want. Something you can do. So the reason why we did that is because we wanted to check how the number of diagrams grow in the case of using off-shell currents from Feynman diagrams, and the other case using IPFT. So and we found that there's a huge reduction in terms of diagrams that appear. So this is the form of the off-shell current. There are many tensor structures. And of course, many of these tensor structures that appear in the off-shell current do not appear in the amplitude classically, because when you contract with the with polarization vectors, so some of them are going to die. So of course, the amplitude is going to be much simpler. So we have also done examples with GR where you have you are interested in a current where you have two external gravitons. In the classical limit, you can also check that the KLT, there's a KLT relation between currents as well, and from that you can recover the Compton amplitude for the spinless case. And you can also do it for spin, of course. As I said, you are only restricted by having a Euler IPFT construction, which we have for spin as well. So you can do that and compute this amplitude. And so we have done that and checked that we recovered results by Saclay and Justin. So, okay, very good. So now, so I'm just going to change gears a bit. So if you have a question about this part.
Perhaps on slide 19, can you maybe I would like to grasp what the diagrams you have. What are those lines?
Sure. When you do the background expansion for and variable, so as I said, it's the perturbation it's controlled by the fluctuation Q. So each of the solid lines represent an order in the equation. So if you have, if you are interested, for example, in this case, 5 external gravitons, what we have is that there is a diagram in which you have 1, 2, 3, 4 fluctuations. So there's a term in expansion in which you have 4 Q's, 4. And so you see that this diagram has as well 1, 2, 3, 4. So all of them are powerful. So now we are gonna change gears. So now we're gonna think about we're now going to be interested in collective phenomena. So and we're gonna think of the plasma. Think about the plasma, which is gonna be made of particles which carry color charge, and the situation in which the particles are far away from each other, so that such that the distance is much bigger than the typical size of particle of the object that is part of the plasma. And so there's a characteristic length that describes this collective phenomena, which is ordered by length. Moreover, I'm also when I think of this problem in the regime in which temperature is very, very, very high, and where I can use as well perturbation theory. So in this regime, I can use relativistic kinetic theory on abelian plasma, something that was developed in the 80s. And so then the description of this plasma, then what we are interested is in having equations that control the distribution functions. And I'm also going to assume that the particles do not collide. So in a typical environment, the particles could collide. In this case, I'm going to consider the system as collisionless, which means that I can focus on the distribution function of a single particle. So this is what's called the microscopic approach to kinetic theory. Okay. And I'm going to consider perturbations around the equilibrium state of the plasma. So as of course, I anticipated from the beginning, but this admits a semi-classical description. So the description is semi-classical because so the distribution function is not going to be classical. It's not going to be classical, so it's going to be also Fermi-Dirac or Bose-Einstein. And so because I'm interested only in a single particle, so I like to have equations in motion for this particle. So the equations for a particle which carry color charge are known as Wong equations, which is shown here. So there's an equation in addition to the equation for the momentum. There's an additional equation for the charge, which now is dynamic. And of course, this is coupled to Yang-Mills. So I have a equation for the current in Yang-Mills, which is given by the top line. So here I'm already thinking about SU3. So there is here the current has an integration of color diffusion freedom, which you can think of this as a trace. So if you more of that, this is just going to do the job of a trace. So then, because the system is collisionless, then the distribution function obeys this theorem, which has the form that I showed here. So, and I can use Lewis' theorem and the equations of motion of my particle to construct the so-called Vlasov equation for the system. This is an equation for the distribution function, which is coupled to the, of course, to the equations of motion of the current. Okay. So I'm also interested in the distribution theory, so I'm going to expand around the equilibrium state. So, and if I do that, I can use my expansion inserted into the Vlasov equation of the system and solve iteratively for f, which then I can use to insert it into my expression of the current, the top line expression. So this, of course, is similar to what we do in the case of just finite zero temperature observable. So eventually, the things that we compute in the classical limit match solutions to some set of classical equations for motion. So this is analogous to that. So then you find that the current can be written in this general form. So after you do this procedure, the iterative solution, in which these objects that appear here multiplying the fields, the dynamic fields, are known as hard thermal loops. These are the hard thermal loops. And the hard thermal loops in thermal field theory can be obtained by considering these graphs that I'm calling COM graphs. So essentially, you take all possible graphs for each gluon, okay, and sum for all of them by taking a forward limit, which means that you close this diagram from here to here. So very good. Now, what would be an on-shell kind of approach for this problem? So, well, of course, it's precisely the answer is off-shell currents. So, but instead of considering the off-shell current, I'm just going to consider the off-shell current in the forward limit. So, in this limit, of course, you are also going to have the diagrams, which are just diagrams are just common from diagrams, but in addition, you are going to have some additional ones. So, and it is regularized because, as probably you know, the forward limit in general is singular, so you have to regularize. So, this regularization, the forward limit is being considered in the context of what is called the root tree duality. So then, so you take your current and then you just take a classical limit of this current. Now, because you now have particles, particle charge, this is subtle. So classical limit. So what is the limit of the classical of a charge, which is quantum? So the answer is something that we worked out here a few years ago, and so essentially starting from IPhT, you can think of the classical color charge that appears in Wong's equations. So, and the procedure to take or the algorithm to take the classical limit is just essentially follows from KMOC. With that, obviously, the important change that this is not an observable. So, so at the end of the calculation, you have to do an analytic continuation to recover target operators. But this is well known in the literature term of field theory. So the analytic continuation is just precisely this way. So the main result is that that this hard thermal loop is just essentially the classical loop of the offshore current. So, so then offshore currents, hard thermal loop can be expressed in this general form. Also do other things. You can think about scalar particles.
It's the same hard thermal loop in the sense of Pisarsky and graphene.
Yes, we did. That's graphene. I don't know. Which I mean, you can play around and think. You can also think about a kinetic theory for biaxial particles, which is interesting. Of course, you can include a spin into this is something that I've done last year. Another relation with the Borland QFT is now straightforward, since precisely this is the object that we were computing before. So there is a matching between the hard thermal loop and the Borland QFT expression for the current. So, as I said, we have checked many theories, GR, 3D, and this where it's known, where the hard thermal loops are known. What is interesting, it's from this Borland theory perspective, we actually have a resummation of all hard thermal loops, and this is what we actually need in computation. So in perturbative, what's called as perturbative hard thermal loop. expansion. So this is what we need, really the transformation that we will end up putting the propagator the way we do effective theory. So, so this brings me to conclusions. So, so what we have seen is that so the current part, we've seen that the coherent wave functions are key to relate both offshore currents and one IPFT. But the same set of ideas are applicable to any theory in which you know what is the partition function of theories, the well IPFT partition theory. Seen that we have experiment that has seen that there's a huge reduction of the number of diagrams. And from that, we have made an additional connection between offshore currents, well IPFT, and icon. So I haven't actually said how to make things with icon. Okay, so of course, people would like to do loops, so as well. So the way, I mean, there's an obvious way of doing loops, which is precisely using the word IPFT formalism, which would be okay, would be straightforward. But so something that would be interesting is instead of doing that, just having a procedure of sawing currents, to construct a higher point classical amplitudes. Which is something that I put in here is classical loops, sorry, classical cuts. So the cut procedures, so the procedure of computing the amplitude from cuts, set of spanning cuts, classical. And doing that, you actually need precisely these currents that the amplitudes that appear in the currents. And other thing that I initial conversations with some people share, but just probably recycle some of the code that is already there to do numerical evaluation of observables. So, yeah, whether or not that's you're doing, already know, because maybe we don't need numerical. But it's something that, in principle, could be interesting. So yeah, thanks for your attention.
We have a lot of time for questions.
About the classical observables in mind.
For what? For higher number of, as I said, I mean, the observables that we have so far is just conservative. Yeah, essentially. Yeah. So the point is that as well as the motivation that we, principally, we don't need more than 5 bytes. So that's 5.
Well, that's not strictly true, right? Because inside, I mean, I'm not quite sure this one is, but let's say as you're doing loop diagrams, then the cuts really involve higher.
Yes. That.
So it's not strict, but I mean, I can't speak to the world standard ones. You will need, of course, in the usual forms, you potentially yourself a wash out, but still it's beyond 5 points.
Yes, exactly. So in the concept of cuts, this story might be relevant. Yep.
Also, this is a little bit tangential, although not tangential to what we're talking about. And things like jet quenching ion equations, and that's not a purely classical effect.
No, you have to.
So
corrections.
You have, but can you still do an expansion about the classical limit and then include? Or is that really truly quantum calculation?
I think that's because in that case your expansion and so I think it's
Yeah,
not,
I don't know really enough on the subject, but how did the hard thermal loops and that whole formula, how does that interact with?
yeah, the hard thermal loop is not it's not really classical. So what I'm saying that the hard thermal loops
Right.
are classical, but the theory of the hard thermal loop is just not really classical. So it's just an expansion in GT, right? G to the coupling temperature.
So you're saying that there are kernels that enter into that, things like the gym walk or the thermodynamic quantities and the quantities which are classical, but then they have to be embedded.
Yes, embedded when you compute the actual observable.
Also, the other thing that's a little bit confusing to me is that the classical limit in QCD also involves taking large representations.
Yes, exactly.
How did that arise in the context of, again, of quark and plasma? Because there are no objects. I mean, are these somehow collective modes that require?
Yeah, there are three collection modes, and in this semi-classical approximation, of course, there is encoded that you take a large representation, not group. So so it is. Sorry, I haven't said mentioned.
No, you mentioned that. But the thing I'm just not understanding in the context of let's say applications of quark and plasma. What are the object with large representations?
Well, the charges, right? Charges of the part. So the description is.
But no, but in a quark and plasma, the objects that are there, you even forget the quarks and the gluons, they just have fixed representation. You don't have particles which are larger and larger representations, larger and larger. So I'm not quite seeing how this interacts with that.
No, but that's what I said, right? So the description of new particle in this context is say the semi-classical description. So these charges that we here actually have.
So these are supposed to be somehow the collective modes of the ones that builds up. Okay. Why did it? From the point of view of the plasma, why is it that the large representation? I mean, sure, if you form whatever balls you want or something, then or collective excitations, then there's going to be a whole spectrum of representations, the tensor products. But why is it that physically the large representations dominate? I understand if the large representations dominate, then you can use this.
So you're asking
why is that? Why is it like that? Anyway,
I don't know.
I understand it's a little bit of expansion to the subject. Still time for more questions if there are any.
You expect also spin to be like a
Yeah, spin is a bit difficult, even so finding your. I mean, the definition of the current spin is it's essentially one extra integration here of the particle when you include spin. Right? But in QED, this is not how people do spin actually in general. So because for in principle to include spin effects in plasma QED, right? You cannot really go to high temperature, because if you go to high temperature, then spin is negligible. So in that case, that's not how really people do spin. But what I've done here precisely is, we know from many works how to actually include spin-off for QED. So there's some motion here and stay again. So then what happens is that when you include spin, so you are still solving these equations, some set of equations, right? But what you find is that there is an ambiguity when you take the massless limit, which in principle this is what we should do. So for spinning particles at high temperature, we should really take the mass to zero, some final. So what happens then if you include spin is that this limit, the massless limit is not well defined, but it's something also that people that to do plasmas with spin find that this limit is not it's not well behaved already in what is called the quantum. So there's a quantum kinetic theory, of course, this of this problem, which resolves this issue of the limit in masses. But this is something that you can also see already in the calculation with spin. So when the particle carry mass, so you can impose a spin supplementary condition, although it's not necessary, as we saw just this paper yesterday. But I mean, imposing the spin supplementary condition, okay. And if you impose it, there's no way of doing it for massless particles. There's no rest frame in that case. So what happens in your kinetic theory is that you end up with some term that is divergent. Giving that.
Okay. Any last questions?
On the last slide, you mentioned the icon. You had an arrow going to W14.
Yes.
That's what relations. Just clear this problem on.
Yeah. So I mean, it's just what I did. I didn't mention. I did mention that. So there's a way, of course, of connecting what we know about the amplitudes in the classical limit and the icon of phase and the partition function. So this is exactly brings you to from the amplitude to the partition function to the icon of phase. I mean, of course, I've mentioned that this so far really should be two dots here. This is what you define as the icon of phase, as you know. So this is what I mean. So there's a way of starting with your offshore current. Then what I showed is that you can construct then the partition function of wall IPFT, and therefore the icon of phase. That's what I mean with this arrow.
You know, as far as I understand, within the WQFC, this, I guess you could define this object, this guy, to be an icon of the
Yes.
log partition function.
Yes.
And you can just make that definition to all others. But,
yes, you could do that. You would find some issues, as you probably know, with that.
Like, and it's been worked out by the foundation. I would like to say one loop, how this thing is the same as other definitions of iconic phase and how you get observables from it.
I don't know if it's being worked out to, I mean, at one loop it is worked out, but I don't know if it is, what's the status of the calculations. Because as far as I know, they are not relying on the definition of the icon phase, but rather on the expression of an observable of this icon phase. So essentially, instead of thinking of the icon phase, you think about the expectation value of some operator, or the impulse, exactly, the anything. So yeah. So yeah, it's not settled. So whether you can actually do the resolution this way. So that's, yeah. Still the projection.
Okay, let's thank Leonardo again.